Good evening, everyone. Am I audible? Am I audible to all of you? Okay, thank you. So, I think we can start today's sessions. This is basically from week 6 content. Week 6, it includes I'm not going to the concept. We will go through the problem. So, in between, we will cover the concept also while going through the problem. And you can ask the doubt in between. Okay. So in the last week, the main things we covered was linear transformation. What is linear transformation and what are all the properties of linear transformation and some theorems regarding the linear transformation and 1-1 map, 1-2 map and the kernel of a linear transformation, range of a linear transformation and the dimension of these spaces. And other than that, what we covered is the direct sum of vector spaces, means two subspaces, and so and so. Okay, so we will cover some one or two questions from each of the section. So first we will start with the linear transformation. So we have seen what is a linear transformation. It is a map from a vector space to another vector space such that it is satisfy two property. That is, t of x plus y should be equal to t of x plus t of y and t of cx should be equal to c into t of x. Okay. Now the two maps are given here. The question is, which of the following is not a linear transformation? Okay, which is not a linear transformation. So first one is the map from R2 to R3 and it is defined as L1 of AB equal to A plus B to A minus B 1. So clearly we can see it is from R2 to R3 for all AB in R2. So is this a linear transformation? Can anyone tell? First one. First one, is this a linear transformation or not? One thing you can check is whether the under addition, that means d of x plus y equal to d of x plus d of y, whether it will be satisfied for this map. One thing you can check. But we have one more property, an easy property of linear transformation. That means it maps the zero element of the vector space V to the zero element of the vector space W. T0 equal to 0. Okay. What is the Okay. If T is a linear transformation from V to W, we know that T0, that means this 0 means the 0 element in the vector space V. Okay. It should be mapped to the 0 element in the W. 0 means the vector space means we have addition, right? Okay, vector addition. In the vector addition, we have a additive identity 0. That is the 0 here. Okay, this 0 is mapped to 0. Okay, now first question is whether this L1 is mapping the 0 element of R2 to 0 element of R3. What is the 0 element of R2? It is 0, 0. Correct? 0, 0 is the 0 element of R2. And in R3, what is the 0 element? It is 0, 0, 0. So the question is, what is L1 of 0, 0? What is L1 of 0, 0? Can anyone tell? Just put it in the, substitute it in the given equation. 0, 0, 1. 0, 0, 1. So, is L1 is a linear transformation? If it is a if it is a linear transformation, it should map 0 to 0. Here, this 0 is not to map to this 0, right? So, this is not equal to 0, 0, 0. So, it is not a linear transformation. Okay, so this is the thing you can check. So, whenever we have some kind of map, if we are adding some constant plus c, something like this there. If c is not a 0, obviously we can say this is not a linear transformation. If it is linear transformation, usually it will be in some form of the linear combination of x, y and all. Okay, not square term will not come, or addition of this constant term will not come. So these kind of things you can just by looking the question, first intuition you can see whether it is linear or not. Okay, and one more way you can verify the thing separately. For example, take it for example, if I am taking L1 of 1 0, if I am substituting the value, what I will get? 1 2 1 1 2 1. So here I am just substituting the value 1 0 to this given map. Now what is L2 of 2 0? If I am substituting again 2 0, A is 2, B is 0. So what we will get? 2 4 1. Okay, 2 4 1. Now what is 2 times L1 of 1 0? That is 2 times 1 2 1. Okay, because L1 of 1 0 we have already seen. That is 2 4 2. So these two are distinct value, right? That is L2 of 2 0 not equal to 2 times, sorry, L1. Oh, sorry, this is L1. L1 of 2 0 not equal to 2 times L1 of 1 0. Okay, if it is a linear transformation, this multiplication should hold like scalar multiplication. L2 of 2 0 equal to L1 of 2 0 should be equal to L1 of 2 times 1 0, which should be equal to 2 times L1 of 1 0. That is not holding in this case, so not a linear transformation. Okay, so A is not a linear transformation. Now what about B? Is this a linear transformation? What do you think by intuition? Is this like you can do separately, like under addition, multiplication, everything you can do. But the question is just seeing this. F means function. Okay, function from CAB. What is CAB? Anyone know CAB? CAB means set of all continuous functions from AB to R. Okay. Okay. What is CAB? CAB is the notation for set of all continuous map from AB to R. Okay. And the map L2 is defined from CAB to C2AB. Again, what is C2AB? So no need to think much on this. I am just specifying what is the spaces. So no need to think much on this space and all. Okay. So set of all F from AB to R such that C2 means F is twice differentiable. That is F dash F double dash. 2 times we should be able to differentiate it. F twice differentiable and F double prime is continuous. Okay, that is C2 of AB. And given the map linear transformation from CAB to C2 of AB is given as T of F. We know CAB means it contains functions. So if we are mapping means T should map the function from the domain. Okay, T of F equal to F plus F dash F minus F dash, correct? Okay. So this is how the function is defined. Now we need to check whether it is linear. So for that we should check under addition and scalar multiplication the respective properties are satisfied or not. So to check these things we can combine these things, scalar multiplication and addition we can combine. How we will combine? T of CF plus G, we should be able to prove this is equal to C into T of F plus T of G. First we will do by definition. What is T of CF plus G? Now F is continuous, G is continuous. So CF plus G, it is also a continuous. Okay. So this is also an element from CAB. So we can apply the T definition to CF plus G. So what we will get? CF plus G plus Cf plus g dash. So in the definition, instead of f, what I am applying? Cf plus g. Now in the same way, Cf plus g minus Cf plus g dash. Okay. Now derivative Cf plus g whole dash, it is same as Cf dash plus g dash, right? So what we can write? Cf plus, or I am not writing all the step. So what we can write? C into f plus f dash okay. So what we need? C times Tf plus Tg, right? This is what we want. By definition, what is this? C times f plus f dash f minus f dash. Tf means f plus f dash, f minus f dash, plus what is Tg? G plus g dash, g minus g dash, right? Now again, if you are seeing what we are doing, we are combining the terms here. Cf plus g, then Cf dash plus g dash, correct? What is this? This is equal to Cf plus g. Okay, next we will take Cf dash plus g dash, Cf dash plus g dash. So that is what we are having in the above step. So this same way, what we will get? Cf plus g minus Cf plus g or Cf dash plus g dash. Fine. So just rearrange the terms from this step to get the next step, and so we can prove T times Cf plus g equal to C times Tf plus Tg. So it is just a matter of calculation, or you can do separately also. T of f plus g equal to Tf plus Tg and T of Cf equal to C times Tf. So in this case, T is a linear transformation. Okay. Anyone having doubt here in this first A and B part? If any doubt is there, please ask. Otherwise, we can go to the next problem. Again, the problem is to find whether the given is a linear transformation or not. So, first question, what do you think? First one is a linear or not? A part, T1 from R3 to R2. We can see XYZ is coming from R3, correct? This XYZ is coming from R3. So, T maps R3 to R2. Here we have two coordinates only. So, this is in R2. Okay. And it is defined like this. First of all, as I told earlier, first we checked whether T maps 0 to 0. In this case, whether T maps 0 to 0, yes or no? T of 0 equal to 0 or not? That is the question. Anyone? So that's an easy thing. Yeah, T of 0 equal to 0. So, but just with that we cannot conclude okay, if T of 0 not equal to 0, we can conclude okay, it is not a linear transformation. But in case T of 0 equal to 0, it can be a linear transformation, but it need not be a linear transformation. So in this case, we should verify the property T of x plus y equal to T of x plus T of y, or T of Cx equal to C times T of x. Now, let us see what is T of 1 0 0. Whenever you are trying, here you can see this is some kind of x square plus y square comma z square. Okay, this is not linear. What does linear means? It is the power is usually 1. Okay, this is coming quadratic terms. So obviously it is not going to be a linear map, but we should prove that it is not a linear map. For that we need some example to say, to give a counter. Okay, So what is t of 1, 0, 0? X is 1, y and z are 0. Okay, so this is the value. Now again, we will consider t of 2 times 1, 0, 0. What is this? T of 2, 0, 0. Correct? So if we are doing t of 2, 0, 0, what is this? X square plus y square comma z square, that is 4 times 0, 0. Now again, what is 2 times t of 1, 0, 0? That is 4, 0. Okay. So the definition is x square plus y square z square. Okay. Now what is 2 times t of 1, 0, 0? 2 times 1, 0, which is 2, 0. So this is not equal to t of 2 times 1, 0, 0, right? 2 times t of 1, 0, 0 and t of 2 times 1, 0, 0, 0 are equal, not equal. Okay. So t not a linear transformation. Clear? Now, in the same way, B. What do you think, whether B is a linear transformation or not? So just by looking observation itself, you can see whether it is a linear transformation or not. First of all, T2 mapping 0 to 0 only. Okay, that is not a problem. Now, is there anything other than linear term comes? It is all some kind of multiples of linear terms of x, y and z. Correct? There is no quadratic term or cubic term or something. Okay. So just by the observation we can say it is a linear transformation, but you should verify what is T2 of x plus y equal to T2 of x plus y, T2 of x plus T2 of y, and T2 of Cx equal to C times T2 of xy. Okay. So the thing is, I am not going to do this example. So B part you can do it as a verify it. It is a linear transformation. So only thing is you need to take is T2 of x1 y1 z1. So x2 y2 z2. Okay. So this summation inside the bracket, it should be equal to, verify this pattern. Okay. T2 of x1 y1 z1 plus T2 of x2 y2 z2. That means linearly we are able to distribute. In the same way, verify T2 of some constant a x1 y1 z1 equal to a times T2 of x1 y1 z1. So this is nothing, it is just like write what is the left side, expand it, write it in terms of the arches. Okay. So that is an easy job, you can do it yourself. Now I think that linear transformation and how to check whether it is a linear transformation and all, it is clear for you. Maybe at the end we will come to some more question like that. Now we will go to the null space. Okay, null space, range and all. So what is the null space? Can anyone tell? What is the null space and what is the range? You can actually just open the mic and just talk, like, because it is, if you are interacting, it will be more useful to you, so that I will also understand where you are having problems and all. So I can focus on those kind of topics more. So that's why I am asking you to, because I don't know whether I am maybe going too fast or too slow and all. So just tell what you know and what you don't know, so that we can go in that speed. Okay. First of all, can anyone tell null space? What is null space of a linear transformation?
Zero element.
Yeah, the elements which is going to zero element, right? Null space means not just zero element, the elements from the domain space which are all mapped to the zero. Okay. So the question here is, let's see the question. T is mapping from R2 to R2. What is the definition? T of AB equal to A0. So this also you can verify if you want. You can verify T is a linear transformation, because this null space, everything is defined for a linear transformation. Verify it. Okay. Now we need to see what is the null space of T. Null space has another name, kernel. Okay, kernel of T. So what is the definition? Null space of T or kernel of T equal to set of all, here the map is from R2 to R2. So we will take set of all AB in R2 such that TAB equal to 0. 0 means here again it is going to R2, so it is 0, 0. Okay, so we need to find all elements from R2 under which the map T, this element is going to 0. Okay, now the condition here we are having is TAB equal to 0, 0. And we already know what is TAB, it is defined. Okay, so what is TAB? TAB is A0. Okay, TAB is given as A0. What we need to find is the all poems in R2 such that TAB equal to 0. What is TAB? A0. That is A0 equal to 0. Right, this is equal to 0. What does that imply? A should be equal to 0. Okay, from this condition what we can extract is A equal to 0. We didn't get anything about B. What does that mean? We can have any values for B. See, from the definition itself we can see B is not at all affected, like the result is not at all affected with B. Whatever B we are taking, TAB is just depends on the first coordinate. Okay, so if we are equating to 0, the only first coordinate is needed to be 0. For example, I am taking T of 0, 1. By definition, what is this? T of AB is A0, right? T of 0, 1 is 0, 0. Okay, if I am taking T of 0, some 0.5. Again, what is this? This is 0, 0. We are not at all checking what is B. It is always A0. So, only thing we require is the first coordinate is 0. Okay. Now, can you say what is the option? Null space of T.
D.
Okay, option D. Okay. So answer should be D. That means, okay, let me write it properly. So null space of T equal to set of all AB such that TAB equal to 0. Okay, in that way we can write set of all AB in R2 such that TAB means A0 equal to 0. That means set of all AB in R2 such that A equal to 0. Okay. Now A equal to 0 means it should be in the form 0 B in R2. So that is what the given 0 A in R. Now we got what is the null space. Now what is the nullity now here? Nullity means the dimension of the null space. Okay. Now tell what is the nullity. That means dimension of the space that we already found here. What is the dimension of this D? Dimension means how many linearly independent set is required to generate, or like the least number of element means
One.
yeah, 1. Okay, okay, 1. So what element will generate it? 0, 1. Okay, 0, 1 is enough to generate the whole space 0 A. So dimension is 1. Okay, that means nullity. Nullity means dimension of null space. It is 1. Okay, now we can very quickly see what is the range of T. We already seen what is the null space and we have seen the dimension also. Now can you quickly say what is the range of T? Out of this ABCD option, what is the range of T? Again, once again, let's recall the definition. Range of T means set of all elements in the codomain R2. Okay, such that T is mapped to that elements. Okay, to where T is going, the image of T. Okay, that is exactly the range of T. What is T? TAB equal to A0. So what are all will be the elements in range? Images. What are all the possible images for any element in R2? What is range of T? Range of T means set of all T of AB such that AB in R2. That is the definition of range of T. Now, out of that, first we will see what is the definition. Okay, what is TAB? TAB is A0 such that AB in R2. So, whatever the element we are taking from R2, we are getting the range elements as A0 form. Okay. So, what is this? This is just A0 such that A in R. A varies from R. We will get all forms A0. So, what is the range? Range is set of all elements in the form A0 such that A is coming from real number. Again, rank of T. Can anyone say what is rank of T?
One.
Yeah, one. Rank of T is again, just as in the earlier case, it is the dimension of the range. So from here we can easily say A0 is generated by just one element 1 0 which is linearly independent. So rank of T is 1. Okay. Okay. Now it is it may seem a bit complicated, but we can go to this question. T is a map from linear transformation from Mn of R to Mn of R. It is defined as T of A equal to A plus A transpose by 2. Okay. First we need to check T is a linear transformation. That's very easy thing. Again I am leaving it as an exercise. Okay. Or if anyone want me to do that, I can do. Otherwise I think it's an easy job because you just need to what A plus B, do T of A plus B equal to T of A plus T of B. Just by observing you can see it will follow directly. Okay. So in the same way scalar multiplication also. So if anyone have doubt, just let me know. Otherwise we will go to the B problem. The question is dimension of null space and dimension of range of T. Okay. Again, here what is Mn of R? Anyone knows? Mn of R. Mn of R means set of all n by n matrices over R. Okay. Mn of R, set of all n by n matrices over R. That means all n by n matrices whose entries are coming from the real number R. Okay, that's all. Now, first question is what is the dimension of null space? Let us, if you are having a question, write the definition first. Okay, null space of T. That means set of all A in Mn of R such that Ta equal to 0. So, we got a condition. What is the condition? A from the matrix n by n matrices such that it maps to 0. So, we will just deal with this condition T of A equal to 0. Now, by definition, T of A is given as A plus A transpose by 2. Okay. A plus A transpose by 2 equal to 0. What does that mean? A plus A transpose equal to 0 or A equal to minus A transpose. Okay. So, what kind of element will be in the null space? If that matrix satisfies A equal to minus A transpose, this equation, if this is satisfied, then what we can say? A belongs to null space of T. That is what we got, right? Now, what is this condition? Star says A is, if A equal to minus A transpose, then
Skew symmetric.
Good. It is Q symmetric. If A equal to A transpose, it is symmetric. If A equal to minus A transpose, it is Q symmetric. So basically what we want to find is the dimension of all skew symmetric matrices. Correct? If it is a skew symmetric matrix, then only T of A is 0. Okay, we proved that T of A equal to 0 when A equal to minus A transpose. In the same way, when A equal to minus A transpose, T of A equal to 0. So we need to find what are all the possible A, that means what is the dimension of the collection of skew symmetric matrices. Now, is that clear, that concept? I hope. Okay. So null space of T is the set of all n by n skew symmetric matrices. Okay, that is what we got. Now to find the, what we need to find is dimension of null space. We got the null space, so we need to find what is the dimension of n by n skew symmetric matrices. So before going to n by n general case, let us see what is happening in 2 by 2, 3 by 3 and all. So you will get the idea. Consider 2 by 2 matrix A, B, C, D. Now, what is its skew symmetric matrix? What we want is A minus A transpose equal. Okay. Now, if I am taking a matrix, okay, I am considering minus A transpose. A, B, C, D. So, this is my A, this is my A transpose. Okay, A equal to minus A transpose. For any matrix, I am considering the equation A equal to minus A transpose. Now, here we will get A equal to minus A and D equal to minus D, the diagonal elements. Okay, you can see the diagonal elements A equal to minus A and D equal to minus D. What does that means? A equal to 0 and D equal to 0. Correct? If positive and negative parts are equal means both are 0. So what we got? If it is a skew symmetric matrix, first of all diagonal entry should be 0. Correct? Diagonal entry should be 0. Now, what we need? We will equate the remaining part. What we got? B should be equal to minus C. So I am equating this and this, and then I will equate this and this. Okay, B equal to minus C, C equal to minus B. So this is basically same equation. Okay, one is the negative of other. So if this kind of A equal to minus A transpose in case of 2 by 2 matrices, this is satisfied for what kind of matrices? Diagonally 0, here some B, here some minus B. Okay, in that case A equal to minus A transpose is satisfied. Okay, so in 2 by 2 case, let us see what is the dimension. What is the dimension of this kind of set? B is in R. Only one variable. So what is the dimension?
2.
2 means we need 2 elements to generate the whole set, the given set, right? Here, but I need only one element. See, what is this? This is equal to span of 0, 1, minus 1, 0. Correct? Whatever B in the 2-1th position, the same B should be in the 1-2th position also. So only one element is the variable. Okay, only one variable, 2 zeros, only one variable, one positive part is in the 1-2 element, negative part in the 2-1th element. Okay, so just one element is required to generate whole A such that A equal to minus A transpose. So dimension is equal to 1, right? Is that clear? Why dimension is 1, is that clear?
Yes, ma'am.
Now let us see 3 by 3 also. Let me write A, B, C, D, E, F, G, H, I. So what we need is A for any 3 by 3 matrices. we are considering the matrices of the form A equal to minus A transpose. So we will equate A and minus A transpose, then we will accordingly do. So this is A transpose A B C D E F G H I. Again you can see in the diagonal actually the terms are same in A and A transpose, and A equal to minus A transpose means along diagonal it should become 0. What we can see here, A equal to minus A, E equal to minus C, I equal to minus I, the diagonal elements. So this should be equal to 0. A, E, I, everything should be equal to 0. Again if we are coming, what we will get? We should equate D and B here. Here also D and B. What we will get? This position D and minus B. Sorry, B and minus D are same. Okay. If we know B, what should be D? It should be the negative of B. Correct? For example, what we are getting? We got diagonal. Along diagonal it is 0, 0. Now, if I am writing B here, it should be minus B here, right? Because of the equation B equal to D, B equal to minus D and D equal to minus B. In the same way, if I am considering G and C, G, C. Okay, C equal to minus G, G equal to minus C. Correct? So, here also, if I am writing some G here, it should be minus G. Okay, now what is this one? H, F. That is F is minus H, I is minus F. Here one minus sign is there, don't forget that. Okay, I and sorry, not I. Okay. So what is this? What we were talking is F should be equal to minus H and here H should be equal to minus F, right? Okay. Now if I am having one element, say F here, here it should be negative of that part. Okay. So all the diagonal should be 0. Whatever in the above the diagonal, the respective negative should be there below the diagonal. Okay. So in 3 by 3 we have 3 variables. What are all the 3 variables? B, G and F. If B is there, minus B should be there. G minus G, F minus F. So these are connected. Okay. So the independent variable is 3 only, B, G, F. So what is the dimension? Dimension should be equal to 3. Okay. So for example, we can very quickly see the basis also. Okay. Basis how we can write a, put B is 1, all others are 0. That is 0, 1, 0, minus 1, 0, 0, 0, 0, 0. What we have done here? B is 1. So minus B is 1. So one term we will get it. Now we will put G is 1. All others are 0. Okay. 0, 0, 1, 0, 0, 0, minus 1, 0, 0. Okay. So the third element will be 0, 0, 1, 0, minus 1, 0. So this will be the basis. Okay. Now we have seen 2 by 2 and 3 by 3. From this we will get an idea how the n by n works. How n by n work we will see. Now if we have an n by n matrices, as in the earlier reasoning, what we got? The diagonal A equal to A minus A transpose. Okay. So the diagonal for A and A transpose are same, whatever the order. So the diagonal should be equal to 0 always. So in this way, diagonal is always 0. Now you can think how it is coming. Okay, because 2 and 3 we have seen. Now if I have one element A here, since A and minus A transpose are equal, here the element should be minus a, correct? Whatever I am having b here, it should be minus b. So it is a kind of whatever we have above the diagonal, the negative part in the below the diagonal. Okay. Now how we will find the dimension of skew symmetric matrices? For 2 we got it is 1. For 3 we got for 3 by 3 matrices we got it is 3. For 2 by 2 matrices we got dimension is 1. In general, in n by n case, what is the dimension? Here we can see. Consider this diagonal. Okay, diagonal means it has n elements, right? All the n elements are 0. That we already see. Now we see the just above the diagonal. Okay, that means this one just above the diagonal, it will be n minus 1 elements, right? Any doubt there? Because in diagonal we have n elements, so just above this it will be n minus 1 elements. Okay, so if this n minus 1 elements, say if it is a some p q something like this it is going, so whatever it is in the just below the diagonal, what we will get? A minus p something like this. Okay, so here just above the diagonal we have n minus 1 variable that actually will cover this portion and this portion. Okay, that is n minus 1 variable we got. So first we got n minus 1 variable. Now we will say this one. Again, one more portion above the diagonal. Okay, so that means something here. Here we will have n minus 2 elements. Okay, that means n minus 2 variable. Correspondingly, the negative part will cover this portion. Okay, so we need to count only the above diagonal portion. So that is, we got n minus 2 variable from this upper side. Okay, so likewise it is going till this point. This is 1. Okay, only one variable remaining there. Corresponding to that, we will get a minus of that part. Correct? So plus etc. plus 1. So how many variables are there? Only we need to consider how many elements are there above the diagonal, because diagonal is 0 and below diagonal is completely depending on what is in the above diagonal. Okay, so that portion total we have n minus 1 plus n minus 2 plus etc. plus 1 elements. So how that many variables are there? Okay, so what is this value? N minus 1 into n by 2. Okay, is that fine for everyone? It may be a bit complicated feeling, but if you are just thinking what is happening here, you will understand the thing. So dimension of skew symmetric matrices is n into n minus 1 by 2. So this skew symmetric matrices forms the null space of our given transformation. What was our linear transformation? A plus A transpose by 2. So dimension of null space of T is n into n minus 1 by 2. Is that okay for everyone? How the
Yes.
okay, good. So we got the dimension of null space. Now we will see what is the next question. Okay, what is the dimension of range of T? There I will suggest you to use the rank nullity theorem, otherwise it will be a bit like complicated, this kind of calculation. We know rank nullity theorem. What is rank nullity theorem? Anyone remembers what is rank nullity theorem? Okay, let me write it. Rank nullity theorem. What does that means? T is a map from V to W and dimension of V equal to dimension of V equal to n. Fine. That means the dimension of this space, not W. Don't go to the image space. Domain. Dimension of V is n. Then rank of T plus nullity of T equal to n. Dimension of this space V. Okay. Now, what we got is dimension of null space we got for T. Okay. Now, what we want is dimension of the range. That means rank. Correct? We need to find rank of T here. And what is the dimension of V here? What is the V here? V is set of all Mn of R. That means set of all n by n matrices over R. What is the dimension of Mn of R? Anyone remembers what is the dimension? Or you can think what is the Mn of R? It is all n by n matrices. How many variables are there? That many. How many independent variables are there? That will be the dimension, right? How many elements are there in a like n by n matrices? N by n matrix. How many entries are there in n by n matrix? N rows and n columns. So how many entries?
N square 1.
Yeah, yes, what?
N square.
Yeah, n square. Very good. Yeah, n square. Very good. Dimension of Mn of R. That is what we are thinking. So, for example, 2 means it is something A, B, C, D. Correct? 2 by 2 matrices means. So, how many variables are there? A, B, C, D. So, what we will write? 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. This is a basis. That means corresponding to each element, okay, corresponding to each variable, we have one element from basis. Okay, so in 2 by 2 case, we have 2 square elements. So 2 square elements in the basis. So in n by n case, that is Mn of R, n by n matrices means in any matrix we are taking, we have n square entries. So each are independent of other. Like if I am choosing first element A11, I can choose A12 in any way. I am not going to depend on A11, right? All are independent. So we have n square possibility. So n square is the dimension of Mn of R. So using this rank nullity theorem, what we can say is rank of T is n square minus nullity of T. Nullity of V we have already seen, dimension of null space, n into n minus 1 by 2. Correct? So it will be n into n minus 1 by 2. So the answer is 2n square minus n square minus n by 2. To see. Okay. N square plus n by 2 or n into n plus 1 by 2. Okay. So without going to what is the range and all, just to find the rank, we can see the dimension of range or rank is n into n plus 1 by 2 using the rank nullity theorem. So rank nullity theorem is very useful to find this dimension of this kind of things. Okay. Now we will see a linear transformation from R2 to R3, and it is defined as T of xy is 3x plus 2y, y x plus y. Okay. Element R2, element from R2 is mapped to an element in R3 as given. Okay. Now we need to find what is rank of T, what is nullity of T, and find a basis for null space and range. If we are getting either nullity or rank, then we can find the other one. For example, if I am finding nullity, I can easily find what is rank using the rank nullity theorem. In the same way, if I am finding rank, I can easily find the nullity also. But not just this, we need to find the basis also. For that, let us see. First we will see nullity. It is a comparatively easy calculation it will be. Okay, so instead of before finding nullity, let us see what is the null space. Nullity means dimension of null space. Let us see what is null space of T. So null space of T means it is the collection of all elements from the domain R2, set of all element xy from R2 such that it is mapped to 0. What is the 0 here? 0, 0, 0 from R3. Okay, it is going to 0 under T. Now, by definition, what is T of xy? T of xy is 3x plus 2y, y, x plus y. So, what is the condition? It should be equal to 0, 0. That is what it says, right? Okay. Now we just need to equate the coordinates and we need to find what is x, y and z. Okay. For that, 3x plus 2y equal to 0. Sorry. Y equal to 0. X plus y equal to 0. Okay. So, from this what we got? Clearly, from this equation we know y equal to 0 and substituting in this 2 we will get x equal to 0. Okay. So, if xy is an element such that T of xy equal to 0, 0, 0, we got xy should be equal to 0, 0. What does that mean? Null space contains only 0, 0. Is that fine? So what is the nullity? What is the nullity here? Nullity means dimension of null space. So the question is, what is the dimension of null space?
1.
No, it is 0, right? Dimension of a 0 space is 0. So that we will take trivially the 0 element. So, but if there is a when we will say some n is a dimension, we should be able to find n linearly independent element which spans the vector space. Okay, here in the null space or here in the given space set to 0, we have only one element 0. 0 itself is not linearly independent. Why it is not linearly independent? I can write 1 into 0, 0 equal to 0, 0, right? The linearly independent means if I am writing as a linear combination of CA plus C1A plus C2B, something like that, both C1 and C2 are 0. But here the constant is non-zero. So set 0, 0 itself is not linearly independent. Okay. So we cannot find a linearly independent subset of this one which generates 0, 0. Correct? So we will take it as a convention that nullity of this is 0. Okay. If nullity is 1 means we can take all the possible, like for example x-axis is have nullity, sorry, x-axis have dimension 1, right? Here the dimension is not 1, it is 0. Okay. Okay, nullity is 0. Now can you very quickly say what is rank? T is from R2 to R3, nullity 0. So what is rank? Rank plus nullity is the dimension of the domain space.
2, ma'am.
Yeah, 2. So here R2 is the domain, R2 has dimension 2. Nullity we got it is 0. So rank should be equal to 2. So that 2 plus 2, 0 will become 2. Okay. So rank is 2. Now find a basis for null space and range. So leave about this case because we will not be able to find a basis for null space now. Now we can find a basis for range. Now we will see how can we find a basis for the range. First of all, what is the range element? By definition, what is the elements in the range? It is in the form 3x plus 2y, yx plus y, right? Range equal to set of all 3x plus 2y, y, x plus y such that xy are from R2. Sorry, xy are coming from R. Okay. So this is the range. Now we will see what is this actually. We can write this element as x into 311 plus y into, I am taking x outside, okay, then coefficient of x as the tuple, 3 tuple, okay. So x into, from first I will get 3, from second it is just y, okay, this is just y, there is no x coordinate. Here 1, that 1 is here, okay. So in the same way, y into 211 okay, that's all right. Okay, so such that x, y in our, what we got? We took a typical element of the range 3x plus 2y, y, x plus y. So we have extracted x terms, y terms separately. So we will get x into 301 plus y into 211. So if I am taking an element, any element from the range, I can write it as a linear combination of these two, right? What is this? This is span of 301, 211, right? What I am writing? I am writing a linear combination of 301 and 211 in the previous stage. So this is nothing but a span of 301 and 211. So this is enough to form the basis, right? Sorry, basis of range, right? Because this generate whole range, and is this linearly independent? Obviously it is linearly independent. For example, if you have two elements, only two elements, if it is dependent, one will be a multiple of other. That problem I have seen it, I have done in the last classes, so I am not repeating. If we have two elements u and v, if they are linearly dependent, then one is a multiple of other. Here in this case, one element is not a multiple of other element, right? So it is linearly independent, or you can verify also. Consider C1 into 301 plus C2 into 211 equated to 0. If you are getting C1, C2 equal to 0, obviously it is a linearly independent set. So that way you can verify it is linearly independent. So we got two elements which is linearly independent, which spans range, and we already know range has dimension 2. So obviously this is a basis. Basis can be, we can take it as 301, 211. Is that fine for everyone? Any doubt in this question? So this is also something the similar question. So maybe if time is there, I will come back to this. Otherwise we can leave, or you can do it as an exercise, because it is very similar question to the previous question. Okay. Okay. Now we will go to next question. T is a linear transformation from R3 to R2. It is defined as T is mapped 1 0 0 to 1 1, 0 1 0 to 2 3, and 0 0 1 to 3 2. The question is T of 2 minus 3 1. What is the value? So if you have understood what is the linear transformation, how it operates in the elements and all, you can very quickly do the calculation. I will give you some 2 minutes to do the calculation. So I will just give you the hint. Write 2 minus 3 1 as the linear combination of this element, given element 1 0 0 0 1 0 and 0 0 1, and apply the definition of linear transformation. That is the only thing, because t at 1 0 0 0 1 0 0 0 1 it is given. So you write this element as the linear combination of these three. You can write it as some c1 into t of 1 0 0 plus c2 into t of 0 1 0, etc. Right? So just try to do this for 1 or 2 minutes and let me know what is the answer out of the given option. Okay, very good. Option A is the answer. So we will very quickly do the thing. So what is 2 minus 3 1? So only thing we know here is the value of t in the basis 1 0 0 0 1 0 0 0 1. Any element in R3 can be written as the linear combination of this basis element. That also we know. So first we are writing it as the linear combination of basis elements, minus 3 into 0 1 0 plus 1 into 0 0 1. Now if we are applying t to 2 minus 3 1, since t is a linear transformation, what we can do? We can use the properties of 2 into t of 1 0 0 minus 0 1 0 plus t of 0 0 1. Okay, now the 1 0 0, t of 1 0 0 is given as 1 1, 2 into 1 1 minus 3 into 0 1 0 is given as 2 3 plus 0 0 1, t of 0 0 1 is 3 2. So I think you can do the calculation. So final answer is the option A. It will come minus 1 minus 5. Just complete the calculation. Okay. So if you are having any value, if you are having the value of linear transformation at the basis, you can find the value of transformation at any point in the vector space. Okay. Okay, now we will go to the next problem. This also we can do very quickly. Given a linear transformation R from R3 to R2, defined as R of ABC equal to 2A plus B, B. The thing is whether it is linear or not. Obviously the linear part is a routine portion. You can prove it is linear. So it is linear. Okay, we can leave that part. The thing is dimension of image, kernel, these kind of things we need to check. Okay. Now first of all, option A, is this possible? Just leave about R of ABC. Okay, what is this map? You leave about that. Just see what is R. R is a map from R3 to R2. Okay. Suppose kernel of R is 0. Okay. If kernel of R is 0, then dimension of the or nullity is 0, right? Okay. In that case, what will be the rank of R? In the, if option A is true, suppose option A is true. Okay. Now we are using the rank nullity theorem. Okay. Rank nullity theorem says nullity plus rank equal to dimension of the domain space. Here kernel of R is 0 is given. So nullity is 0. Correct? Nullity is 0. So what is rank of R? That is my question.
3 ma'am.
Yeah, it should be 3, right? If kernel is 0, rank should be 3. Then only 0 0 plus 3 equal to 3, which is coming from R3, correct? Is that possible? Rank 3 is possible or not in this case? Don't look at the, you can do with this definition also, but I am not saying don't look at this definition. Just see what is this one, R equal to R3 to R2. Okay, if A is true, we got rank should be equal to 3. Rank 3, is this possible or not? Rank means dimension of range. Range is a subspace of which space here? R2, right? What is range? Range means set of all R of x in that form. R is mapping from R3 to R2. That means set of all R of x is actually a subspace of R2. That is our range. Can this range can be dimension 3? No, right? Very good. No, because range, we already seen range is a subspace of this space R2. So it can be dimension 0, 1 or 2. It cannot exceed 2 because it is a subspace of R2, right? So just without looking this only, we can say this option is false. If kernel is just 0, then nullity is 0. Rank is 3. Rank 3 means range has dimension 3. It is a contradiction to range is a subspace of R2. That is the thing. In the same way, without looking at the definition, we can see B. B is again what they are saying, dimension of image of R. Image of R means range of R only. Okay. Again it is given, sorry, dimension means it is not set. It is 0. Dimension is given 0. Okay. Now, what is nullity here? If dimension of range is given as 0, what is the nullity? Again think about the rank nullity theorem. What is the nullity? 3. Yeah. Because nullity plus rank is 3. Okay. Here rank is given as 0 in the option B. So nullity should be 3. Again I am saying nullity is 3 means it comes whole R3, right? Nullity 3 means dimension of null space is 3. And the null space is a subspace of R3. Okay, we are collecting all elements from R3 which is going to 0. So it is obviously a subspace of R3. Okay, and we got that dimension of that subspace is 3. That means that null space is same as R3. That is not possible because our R is not a 0 map. The null space is 0. Sorry, null space is R3 means all elements in R3 are mapped to 0, 0, 0 like that. Since R is not a 0 map, this option can also be discarded. Okay. Now, linear but not 1, 1. Now, this is the only option we are having. Linear part is fine. Again, whether it is 1, 1 or not. Can you see whether if it is 1, 1, only 0 will map to 0. Okay, that means kernel is just 0. That is the first case. If kernel is 0, this condition is satisfied, then it is 1, 1. Okay. So, already we have seen that is not the case. If that is satisfied, some contradiction is coming. So, obviously it is true. Okay. So, what basically says is, other than the element 0, there is an element in R3 which is going to 0. Okay. So, my question is, find ABC a non-zero element such that T of ABC equal to 0. So, T is the, or not T, sorry. R of ABC. Okay. R of ABC is given. I want you to give a element, non-zero element, which maps to 0. Can anyone tell? Very good. 0, 0, 1. Because in the image we can see it is just depending on A and B. C can be any value. Okay. So for example, if we are taking 0, 0, 1. What is by definition? It is 2A plus B, B. A and B are 0. So obviously it is 0, 0 here. So it is 0, 0, not 0, 0, 0. Okay. Okay. So we got an element R0, 0 equal to 0, 0 and R0, 0, 1. Instead of 1 you can use any like 2, 3, 4, any constant you can, non-zero constant you can use. But 0, 0, 0 not equal to 0, 0, 1. This is the condition of not 1, 1, right? F of A equal to F of B implies A equal to B, or not like this. This implies this. A not equal to B, but F of A equal to F of B. So it is not 1, 1. Okay. So yeah, about this kernel dimension of image of R and all, you can just go to R of ABC. You can find what is kernel, what is the image and all, and then also you can verify this option A and B are false. Okay. So as an exercise you can do in a that alternative way also. So if you are doing this kind of questions, it will like improve this your thinking capacity. Okay. Now, next question is, okay, we have seen to write a linear transformation in the form of a matrix. Okay, in the class we have seen that. So I will just, oops. Okay, I will just recall how it will be written. If T is, we can do this question, or maybe this may be the first kind of question you are seeing. So, given the map T of XYZ is from R3 to R2 is defined as x plus y, y minus z. Okay. To write the matrix of T with respect to the given ordered basis. So what does that mean? That means first we should write T of 1, 0, 0, T of 0, 1, 0, T of 0, 0, 1. By definition, what is this value? Okay. What we are taking? We are taking these three elements 1, 0, 0, 0, 1, 0 and 0, 0, 0, 1 from the basis, given basis of R3. Okay. Now, under the function, it goes to x plus y, y minus z. X plus y, y minus z, x plus y, y minus z, x plus y, y minus z. Okay. So, we got these three value. Now, what we will write? We will go to the second basis. Now, it is an element of, we mapped an element of R3 to R2, basis element of R3 to R2. Okay. Now, whatever we got the R2 elements, we will write it in terms of the linear combination of the given basis 1, 0, 0, 1. So, how we will write it? We can write it as 1 into 1, 0 plus 0 into 0, 1. In the same way, 1 into 1, 0 plus 1 into 0, 1. 0 into 1, 0 minus 1 into 0, 1. Okay. So, this is the first step. After writing this, what we will do is, we will collect the coefficient and write it in a matrix form. For example, the given matrix B1, B2. Okay, we will write this with respect to the matrix B1 and B2. Okay, this is the way of writing. How we will write is, first we are having this one, right? We will collect the coefficient. What are the coefficient? 1 and 0. It should be in the same order. Here the order is given 1, 0, 0, 1. So we should not change the order. So in the same order, we will write it in the column 1, 0. Again, next 1, 1, 1, 1, 0, minus 1, 0, minus 1. Okay. So this is the required matrix. Clear? So this is how we will write the matrix form. In the same way, B also we will do very quickly. So I have done A for your understanding. B, it is not a standard basis, right? So it may be a bit difficult. It is not that difficult, but still it may be a bit difficult to write it as a linear combination of basis and all. So what is T of 1, 1, 1? Here see, earlier we were doing the basis element 1, 0, 0, 0, 1, 0, 0, 0, 1. Now in the B option, given basis is this one. So what we will do? We will take the elements from the given basis. Okay. And the equation is x plus y, y minus z, which is equal to x plus y, y minus z. And what is T of 1 minus 1, 0, 1 minus 1, 0, x plus y, y minus z. And the third element is 0, 1, 0, right? 0, 1, 0, x plus y, y minus z. Fine. So we have written. Now what we need? We should write the given 2, 0, not the obtained 2, 0, 0 minus 1, 1, 1 in as the linear combination of this basis. Not the earlier basis, not the standard basis, the given basis 1, 1, 1, 0. Okay. How we can write it? This is easy. 0 times 1, 1 plus 2 times 1, 0, right? Okay. Now what we can write? Minus 1, 1 plus 1, 0, right? 0 minus 1. Okay. And 1, 1 means how we can write? Okay. 1 times 1, 1 plus 0 times 1, 0. That is enough. Okay. So in the same order, 1, 1, 1, 0, that order only we have to write. Now we need to write the matrix form. It should be 0, 2, minus 1, 1, 1, 0. Okay. So this is the matrix. So you can see both matrices are different. The reason is the basis changed. If at least one basis is changing, still the matrix will differ. So the matrix is with respect to the given basis. Okay. So when we usually write linear transformation in matrix form, usually it will be the standard ordered basis. So this is the standard ordered basis for Rn. Okay, first one. Okay. Standard ordered basis. So usually we will write this is we are doing for some kind of exercise. Okay. Yeah. Now this problem is a very trivial problem. We will do very quickly. It is given a subset V1, V2, etc. Vn of V. Okay. V is a vector space. So the question is span of S is a subspace of V. For that what we want to prove is if we are taking x, y in span of S, what we need to prove is Ax plus y belongs to span of S. Okay, that is what we want to prove. So this we will prove when S is a span S is a non-empty set. Obviously span S is a non-empty set because span S contain S. Okay, already this V1, V2, etc. Vn all will be in V1, V2, etc. all will be in this span of S. Okay, so it is a non-empty set. This non-empty set is a vector space. If two elements we are taking from the set, the linear combination should also be there. Now x and y belongs to span S means x is some a1 b1 plus an bn, some linear combination, and y is some b1 v1 plus etc. bn bn. Now it is an easy job to do here. What is this? A into a1 v1 plus an bn plus y. Y is b1 v1 plus bn bn. Again we can write it as a1 plus b1 into v1 plus etc. an plus bn into vn. Obviously this is from belongs to spans. Okay, so that's all. This is a very trivial question. Okay, I hope things are clear for you. If it is not, you can ask. Now it is a one more standard question. F is a field and V is a vector space over the given field F, and V is defined as the collection of all polynomials from F into F. So how the polynomial will look? F of x is c0 plus c1x plus ck x power k, right? Now the question is, if D is an operator defined as V to V such that it is the differentiation operation. That is, what is that? Df of x means derivative of f. What is the derivative of f? F is c0 plus c1 means c1 plus 2c2x plus kck x power k minus 1, correct? First question is to verify D is a linear transformation. That is in again Cf plus g. What is this by definition? Cf plus g dash. Cf dash plus g dash c into df plus dg. Or you can take two polynomials, separate polynomials, write it in this form, means f of x, g of x, write it in the form, in this form, and add it, differentiate it, and separately differentiate, prove that they are equal. So both are okay. So remaining thing you can do it as yourself. So we will go to more serious part of this question, that is describe the range and the null space of the transformation. First, as usual, we will go to the null space. It is comparatively easy. What is null space? First we will give the definition. Null space of D equal to set of all polynomial such that f dash x. What is the operation derivative, right? D means d of f means f prime of x equal to 0. For which kind of polynomial derivative will be 0? Those kind of polynomial will belongs to null space. So can you tell what will be in the null space?
Constant polynomial.
Yeah, very good, constants. Okay, so constant polynomial, otherwise it will not be 0. If x, x square, all terms are there means it is not 0, right? So all the constants are in the null space. So what is the nullity? 1, right? Dimension of null space. That means constant means 1 will be there, 2 will be there, 3 will be there, 0.5 will be there, everything will be there. Okay. So just one element is required to generate all the elements, that is the basis. So nullity is 1. Now null space is fine. What is the range of the linear transformation? Can anyone guess what is the range of the linear transformation? The map is from V to V, that means set of all polynomials to set of all polynomials, because you can see f dash x is again going to be a polynomial, right? F is a polynomial, f dash is a polynomial. So basically the range is actually the whole space, it will come the whole space. Let us see why it is coming. Now let me take any element a0 plus a1x plus a2x square plus etc plus anx power n. Okay, so this is an element from V, that means a polynomial. Okay, if I am able to find an f of x, suppose this is my g of x. If I am able to find an f of x in V such that df equal to g, then I am done, right? That means all elements in V has a pre-image. That means every element is like some image of some element from V. Okay. Now, how can we define such an f? There should be an f such that df is g for any polynomial g. For example, let us see. If I am taking f of x equal to a0 x plus a1 x square by 2 plus a2 x cube by 3 plus etc. an x power n plus 1 by n plus 1. Now, what is derivative of f dash? What is the derivative of f dash?
G of x.
Yeah, g of x. That means df equal to g, and g we have taken an arbitrary element for any element in V. For any polynomial we have something, okay, some f such that df equal to g. What does that means? D is an onto map. What is onto map means? Onto map means D covers all the codomain. Okay, that means range is same as the codomain. Codomain equal to V. Okay. So here we got nullity is 1 and rank we cannot say here because it is an infinite dimensional space. For example, what is the 1x, x square, x cube, etc. All these are linearly independent set in the space. So we cannot say like rank because it is something infinite. So we can say kernel is just like it has dimension 1 and the range is actually the whole space. Okay. Okay. Now one more question. This is again a use of rank nullity theorem only. The question is linear transformation is given from R11 to R13 and it is given, it is 1 1. If it is 1 1, first question is what is kernel of T? Can anyone say what is kernel of T or rank of or nullity? Kernel of T or nullity, anything? Given T is 1 1, if it is 1 1, then kernel of T is 0. Good. Kernel of T is just 0 element. 1 1 means no two element map to same, right? So 0 obviously map to 0. If one more element, non-zero element map to 0, it will not become 1 1 map. Okay, that is why when kernel of T, that is why when it is 1 1, kernel becomes only the 0 set. Okay, so we got kernel of T is just 0 element. That means nullity is 0. Now, can you say which option is correct out of this? Now it is an easy job. We got what is nullity. Now only thing is to find rank. So out of this, which one is correct? A, B, C, D.
D.
Yeah, very good. Because rank and nullity should add up to 11 because R11 is the space, it has dimension 11. So rank should be equal to 11. So option D is the correct answer. Okay. Yeah, this is again a repetition. Let me just ask you. Kernel is a linear transformation from Rn to Rm. Then it is a subspace of Rn or Rm, Rmn, Rm plus n. Which one is the correct answer? Kernel is a subspace of which space? Domain or codomain? That is the question. Think from the definition of domain. That means Rn. Rn is the domain here, right? So option A is the correct answer. Kernel is a subspace. So what is the second question? Range is a subspace of which space? Obviously it is Rm, right? Range means it is going to Rm. So it should be a subspace of Rm. Okay. Now again the question is you can use the rank nullity theorem. T is a map from V to V and given dimension of V is 9. How many different pairs of AB are possible such that A equal to nullity of T nullity of T and B equal to rank of T. Use the rank nullity theorem and think what are all the possibility for ABs like this. Only thing is A plus B or rank plus nullity equal to dimension of V. What is that? Can you tell? Nullity of T plus rank of T should be equal to dimension of V. Given dimension of V is 9 and nullity of T A, rank of T equal to B. So how many AB are possible such that A plus B add up to 9? That is the only question underlying in this, correct? So how many are there? Can A negative or B negative? From where A and B can start? Can it be negative or can it exceed 9? Anyone? Answer? What is the answer? Like options are given here, 81, 100, 10 and none of this. Okay, the only thing is we need to find the pairs AB such that A plus B equal to 9, right? So what are all the possibility? It can be 0, 9. Okay, that means nullity is 0 and the rank is 9. That is possible, right? If it is just an identity map, obviously rank will be 9, nullity will be 0. In the same way, 1, 8, that is also possible. Like in that way we can construct the linear transformation actually. Okay, that means dimension of V is 9. Okay, that means 9 basis elements are there. Okay, out of that first element I am mapping to 0, all other I am mapping to itself. So rank will be 8, nullity will be 1 because only one element I am mapping to 0 like that. Okay, 180 is possible, 2, 7, etc. up to 9, 0. Obviously this 0, 9 and 9, 0, these pairs are different. Here 0 is nullity and 9 is rank. In the last case 9 is nullity, 0 is rank. So 0 to 9 it varies. So total 10 possibilities are there. It's very easy. Okay. So 10 possibilities are there for the pairs AB. Is that clear? Okay. Now the same question only. What I am saying is we have seen. Okay, you may have doubt. Is this possible to have? Even though I have given a hint, it is possible to have all this possibility. In this question, we will say if A and B are non-negative integers, that is 0, 1, 2, something like that, such that A plus B equal to n for some n greater than or equal to 1. Construct a linear transformation T from Rn to Rn such that nullity is A, rank equal to B. So the previous question will be more clear after doing this one. Okay. Let us see. What is Rn? Rn is the span of E1, E2, etc. En. This is our standard basis. I hope you know the notation. E1 means 1, 0, 0. E2 means in the second position 1, all others are 0, etc. En means 0, 0, etc. 1. Okay. And it is given A, B are some non-negative integers such that A plus B equal to n. Okay. So obviously 0 less than or equal to A less than or equal to n. We know A plus B equal to n. So we are considering the first A terms. It can be 0 also, but out of this, say 1, 0, 0, 0, 1, 0, etc. 0, 0, 1. Out of these, first 8 terms I am taking. Okay, first 8 terms I am taking. Then T of 1 0 0, this is I am mapping to 0. T of 0 1 etc. 0 is 0, etc. like that. What I am doing is mapping E1, E2, etc. EA. Total 8 terms I told. Okay, EA to 0 element. That means this E1, E2, etc. T of EA equal to 0. So first the A elements from the basis are mapped to 0. That means these are all in the kernel, right? Kernel means set of all elements which are mapped to 0. So obviously these A elements are there in kernel. Okay. Now I should assure that this is the nullity. That means already we got A. So there should be no other element in the kernel. So what I have the remaining elements from A plus 1 to B. So T of EA plus 1 is EA plus 1. Okay, etc. T of En equal to En. That means I am mapping the identity wise from there onwards. Is that fine? So obviously these are all EA plus 1 to En does not belongs to kernel. Okay, so we got kernel contains the elements E1 to EA and range contains the element EA plus 1 to En. Okay, so how will be the map? If I have T of x1, x2, etc., xa plus 1, etc., xa plus 1, etc., xn. So these are our A elements. These are our B elements since A plus B equal to n. Okay. So what is this T of x1 E1 plus etc. xa EA plus xa plus 1 EA plus 1, like this we can write. Okay. xn En. So what is this? x1 into T of E1. T of E1 plus etc. xa into T of EA plus xa plus 1 T of EA plus 1 plus etc. xn T of En. Since using the linearity of T, I am expanding like this. Now we know T of A1 is 0 up to T of AA is 0. Okay, so first 8 terms are going to be 0. So how will be the linear map will come? xa plus 1 and T of TE of A plus 1, it is going to itself. In that way we have defined here. Okay, after EA, everything is a kind of identity map. So XA plus 1, EA plus 1 plus etc. xn En. What is this? 0, 0, 0. XA plus 1 etc. xn. So this is the first A elements. So this is the next B elements such that A plus B equal to En. So obviously we got from by the definition only we got the first E1, E2, etc. EA are going to 0. So it is going to be the kernel and all the remaining elements we have here B elements, right? In the range we have B variables. Xa plus 1 to xn means there are B elements, that is the variables. Okay, so that means range will have dimension B. So rank will be equal to B and nullity will be equal to A. Okay, is the concept is clear? Even though you have not understood like what it is exactly the function is defined, if the concept is clear what it is doing, the first A elements are going to 0, others are going to itself. So the first A element form the kernel, so kernel is A and the other elements is contributing to range, so the remaining B forms the rank. Okay, so A plus B equal to N with A is nullity, B is rank. Is that fine for everyone? Okay. Again, this is also something similar we have done earlier. Does there exist a linear transformation from R6 to R2 such that nullity is 2 and rank is 4? This is an yes or no question. So, if you are checking the rank nullity theorem, it is okay, rank plus nullity, 4 plus 2 equal to 6, that holds. That is not a problem here. Is there any other problem occurs? If nullity equal to 2, is it going to give some problem for us? Or if rank is 4, is this going to give us some problem? Or just say what is this, yes or no, is this true or not? Can we find a linear transformation with this given condition? That is the question. Think this null space, range, everything are subspace of which space? Okay. So in that way you can say whether there exists a transformation of node. Okay, what is rank? Rank means dimension of range, and range is a subspace of R2. Now, just after this statement, now you can say easily, does there exist a linear transformation? Yeah. So this is not possible, right? So obviously this is not possible because rank is given 4, that is dimension of range equal to 4. Okay, it is a contradiction, it is a contradiction to range is a subspace of R2. Range is a subspace of R2, so range can have maximum dimension 2 only. Okay, so if it is 4 means it is not possible. So in the same way, nullity equal to 3, rank equal to 3. This is also not possible. Okay, now only thing is rank should be less than 2. When rank is 2, if rank is 3 also it is not possible. When rank is 2, rank is 1, in that case actually there may exist. Okay. Okay then. So okay. T is given from Rn to Rn, a linear transformation. The question is, which of the following statement implies that T is a bijection? So we need to prove that using which of this following we can prove T is a bijection. That is, T is both 1, 1 and 1, 2. First of all, does the A statement imply T is a bijection? It is saying nullity of T equal to N. That is, kernel has n linearly independent elements. Correct? Nullity means from here what you will get if nullity is n? Is this 1, 1 if nullity is n? What we have seen nullity, sorry, the transformation is 1, 1 if and only if nullity is 0, right? T is 1, 1 if and only if null space is just 0. Okay, if some non-zero element is there, it will not become 1, 1. It is a trivial result. Now, what here saying nullity is n, that means null space is not 0. Other some non-zero elements are there. So, A implies T is not 1, 1. So T is not a, if it is not a 1 1, obviously it is not a bijection. Bijection means both 1 1 and 1 2. Now what about B? Is this option B is possible at all? T is from Rn to Rn and they are saying rank plus nullity equal to, rank equal to nullity equal to n. Both rank and nullity is n. Yeah, that is a contradiction to rank nullity theorem, right? If it is both are n, rank plus nullity equal to 2n, that is not true. Rank plus nullity should be equal to n. So B is a contradiction to rank nullity theorem. And the third option is just the statement of rank nullity theorem, rank plus nullity equal to n. And this is true for any transformation, not just bijections. Okay, that we know it is true for any transformation. So C true for any transformation, any linear transformation. Okay, now obviously your answer should be D. So what we want to prove is, using D we should prove T is a bijection. Okay, now what we have T is a linear transformation. So obviously it is satisfy rank of T plus nullity of T equal to n, since Rn is the space. Okay, now again the given condition D is rank of T minus nullity of T equal to n. Rank of T minus nullity of T equal to n. So if we are adding these two, 1 and 2, what we will get? 2 rank of T equal to 2n implies rank of T equal to n. So rank of T equal to n means what? The range, dimension of range is n. So what is range? Range is Rn. Dimension of range is n means range is Rn, right? Because range is a subspace of Rn and we got it has dimension n. So range should be equal to Rn. So that implies onto. Range is whole space means onto. Now what about 1 minus 2? 1 minus 2 means 2nt equal to 0 or nt equal to 0. So this implies 1 1, as we already told. T is 1 1 if and only if null space is just a 0 space or nullity is 0, correct? So we got both 1 1 and onto. So T is a bijection. So these two conditions together, that means this is coming for a very transformation and this we got from the given question. Okay, so we got T is a bijection in this case. Okay, we will do one more question here and then we can stop, I think. So we have already seen if it is a bijection, we will have an inverse, right? Okay, here the question is T of x1, x2, x3 equal to 3x1, x1 minus x2 to x1 plus x2 plus x3. So first we need to check whether it is a bijection. Given it is a linear operator. What is linear operator? Okay, linear operator means T from V to V. So we usually will say a transformation from a vector space V to another vector space W. Okay, so here operator means we are just dealing with a transformation from the same space to the same space. Here it is on R3 instead of V, it is R3. Okay, now let us very quickly see what is in the kernel of this T. T of x1, x2, x3 equal to 0 means each of the coordinate is 0. That is 3x1 is 0, x1 minus x2 equal to 0, 2x1 plus x2 plus x3 equal to 0. So from here we will get x1 equal to 0 and from here we will get x2 equal to 0 and this implies x3 equal to 0. Correct? Just solving the equation. So what we got? Kernel of T is just 0 0 0. Okay, that means nullity equal to 0, or what we can say nullity is 0, kernel is 0 0 means it is 1 1. Okay, and rank equal to 3 using the rank nullity theorem again, because 0 plus 3 equal to 3. 3 is coming from this R3. Okay, rank equal to 3 means range is same as our space codomain R3. That implies onto. Okay, 1 1 and onto means T is a bijection. If it is a bijection, what we can do? We can find the inverse. So what we need to find is, if T of x1, x2, x3 equal to ABC, suppose, then what we need to find is T inverse of ABC. What is this value? Okay, that means we know T of x1, x2, x3 equal to ABC. So we need to find the inverse image of the map T. Correct? Now, what is T of x1, x2, x3? It is given, it is 3x1, x1 minus x2, 2x1 plus x2 plus x3. Okay. So, this should be equal to ABC. Now, we need to solve this x1, x2, x3. That what we want to find is T inverse of ABC equal to x1, x2, x3. We need to solve x1, x2, x3, okay, in terms of A, B and C, correct? So 3x1 equal to A implies x1 equal to A by 3, and x1 minus x2 equal to B implies x2 equal to x1 minus B. From earlier we have x1 is A by 3 minus B. Now next one is 2x1 plus x2 plus x3 equal to C. I am not going to do the calculation, let me just write the. Okay. So it will come C minus, you can do the calculation, x3 will come C minus A plus B. Okay, so what is T inverse of ABC? So we need to put the value x1, x2, x3 here. So what was x1? x1 is A by 3, A by 3 minus B, and x3 is C minus A plus B. So this is the inverse of the given T. Okay. Okay, I think let's stop today. It's enough. Okay, any doubt in today's class? If anyone is having doubt, you can clarify now. Otherwise, we can stop. I think it's like almost time. So no need to go further question, I think. Okay, okay, then we will stop for today, and we will meet again in the next week, same time. Okay, yeah, thank you all. Let me close the meeting.